So in section 12.1, we want to learn what the words maxima and minima are and know how they're used in calculus. So in other words, we want to show how calculus can lead to this concept of finding a maximum or minimum value of a particular function. So let's start out with some definitions to make sure we are on the same page. F has a relative maximum at R if there is some interval R minus H to R plus H for which f of R is greater than or equal to f of x for all x in that interval for which f of x is defined. Okay? F has a relative minimum at R if there is some interval R minus H to R plus H for which f of R is less than or equal to f of x for all x in the interval R minus H to R plus H for which f of x is defined. What the heck does this mean? I'll explain what this means down here on this graph so you can actually see it. Now, one thing to note before I show you that is that relative maxima and minima are called relative extrema. Okay, now let's look at this graph and find out which are relative maxima. Maxima is just plural for relative maximum. Minima is just plural for minimum. Okay, so notice that a relative maximum occurs whenever we're able to take some open interval around a point, and that point is the highest point in that interval. So looking at our example here, we can see that, hey, this looks like a high point, this also looks like a high point, and so does this one. But the only issue with this one is if we were to take an open interval around it, there's really nothing on the right side of it. There's nothing over there. So we cannot say that B would be a relative maximum according to the definition. So our relative maximum, notice that P, if we take a look at P here, that's a high point. Can we take an open interval around P and still have that this point P is the highest in that interval? Absolutely. So that means P is a relative maximum. Can we do the same thing for R? Absolutely. So that means R is also a maximum, a relative maximum. Okay, so now our relative minimum. Our relative minima, well, it looks like A would be 1, but for A, we have the same issue. There's nothing to the left of it, so we can't do that. According to the definition, we have to be able to take an open interval around it. So we now consider the points Q and S. Will they be relative minima? Absolutely, because we can then take the little open intervals around those, and that would be the lowest point in those open intervals. So Q and S are relative minima. Okay, now if we want the highest points on, and the highest point, that would be the absolute max. And then if we want the lowest point, that would be the absolute min. I'll define those on the next page. Okay, we can go back and we've already identified them. Our minimum, absolute minimum is A, our absolute maximum is B. So F has an absolute maximum at R if f of R is greater than or equal to f of x for every x in the domain of your function. So if it's the largest point in your graph. F has an absolute minimum at R if f of R is less than or equal to f of x for every x in the domain of f. Absolute maxima and minima are called absolute extrema Okay, now to identify the absolute max and min from example 1, so our absolute max was B and our absolute min was A. Now, a new concept that would be very helpful for us moving on is that of a critical point. A critical point of a particular function is a point where the derivative is 0 or where the derivative is not defined. Okay? A critical point of your function is a point where the derivative of x is 0 or the derivative of x is not defined. So if I ask you to find your critical points, that implies you have to do two things. Well, three. You have to find your derivative, that's one. Then you have to find out where your derivative is 2. Derivative is not 2. Derivative is 0. That's the second thing. And then you have to find out where your derivative is not defined. That's the third thing. Okay? Now, some terms. If you're finding out where your derivative is 0, that's called a stationary point. If you're finding out where your derivative is not defined, that's called a singular point. Now, critical points, and this is an important fact, critical points and endpoints are where your extrema occur. Critical points and endpoints are where your extrema occur. So if you have a relative max or a relative min or absolute max or an absolute min, it's either going to occur at a critical point or an endpoint. Okay? So now let's look at some examples. So for example 3, we want to find the relative and absolute extrema for f of x equals negative 2x cubed minus 3x with the domain, the closed interval negative 1 to 1. So negative 1 and 1 are endpoints. We want to find the relative and absolute extrema. Well, in order to find them, we need to find our critical points. Okay, so let's find our critical points. Remember, critical points requires us to know what our derivative is. So first, let's find our derivative. F prime of x is equal to negative 6x squared minus 3. Okay, now we need to find out where that derivative is equal to 0 or where it's undefined. Well, that means negative 6x squared minus 3 is equal to 0, or that means negative 6x squared is equal to 3, or x squared, divide both sides by negative 6, which means x squared is negative 1/2. Well, x squared can't be negative 1/2. We can't take the square root of that without getting an imaginary number, so that means there's no solution here. So we cannot have it equal to 0. Well, if we look closely at our derivative, we don't have any issues for any other numbers in our domain, which means it's always defined. It's a polynomial, so it's defined everywhere. So here, note that f prime of x is always defined. So we got no solution when we set our derivative equal to 0. We got it was not always defined, which means there are no critical points. So there are no critical points in the domain. That is an M. Okay? So we only have the endpoints. So now we have to consider the endpoints. Because we know by this fact here that critical points and endpoints are where your extrema occur. So now we need to find f of negative 1. Negative 1 is an endpoint. We also need to find f of 1. 1 is also an endpoint. So we take negative 1 and we substitute that into f of x, not your derivative, into your original function. Substituting -1 into your original function yields -2 times -1 cubed. Let's make that better. Cubed minus 3 times -1. -1 cubed is -1, so this becomes 2 plus 3, which is 5. F of 1, we substitute 1 into our function, and we get -2 times 1 cubed minus 3 times 1. That's equal to -2 minus 3, which is -5. So it turns out that we have the absolute max is 5, or the point when x is -1 and y is 5. Our absolute min, or absolute minimum, is -5, or 1 -5. Okay? And that's our final answer. Okay? All right, now we want to find relative and absolute extrema for the following function. H of x is equal to x plus 1 raised to the 2/5 with the domain, the closed interval, -2 to 0. -2 and 0 are our end points. So now if we want to find relative and absolute extrema, we need to find the derivative of this function. And then after we find the derivative of the function, we need to find the critical points. So the rule of thumb, what we're doing here, so the process, find the derivative, find the critical points, test your endpoints, and then identify all of our information that we need to find, the relative and absolute extrema. Okay, there we go. So let's differentiate. So h of x, h prime of x, is equal to 2/5 times x plus 1 raised to the 2/5 minus 1. That's equal to 2/5 x plus 1 to the -3/5. Okay, we can rewrite that as 2 over 5. That's for the 2/5, and then we can write the 5th root of x plus 1 cubed. So remember, we went over this rewriting before spring break. The 2/5, that's your 2/5. This is a negative exponent, which means this entire part here can go in the denominator. That denominator here in the exponent means it's the index. So the 5th root of this cubed. Okay, there we go. So that's our derivative. Now we need to find our critical points. So that was step 1. Step 2, we want to find our critical points. So we set our derivative equal to 0, and we see if it is ever possible. That equals 0 when we have 2 over 5 times the 5th root of x plus 1 cubed equal to 0. But note that, so note a over b equals 0 if and only if a is 0. So in other words, if our numerator is 0, can 2 ever be 0? No. 2 cannot be equal to 0. Okay? So note that if we go back, the numerator is never 0. So there's no solution for that part. Or we say that there are no stationary points. Either way. Now, you can also have critical points whenever you have your function is undefined. So we have to consider that. H prime of x. So that's one part. To finding your critical points. The second part is to find out when this is undefined. Well, this is undefined when our denominator of our derivative is 0. So in other words, when 5 times the 5th root of the quantity x plus 1 cubed is equal to 0. And the reason it would be undefined is because we cannot divide by 0. So we solve this. So now divide both sides by 5. 0 over 5 is 0. So we have the 5th root of x plus 1 cubed equals 0. And then we raise each side to the 5th power. And we get x plus 1 cubed equals 0. Well, that means if we take the cubed root of each side, cube root of 0 is 0. So we have x plus 1 equals 0, or either you can take the parentheses off, and then that gives us x equals -1. That will be a singular point. That is a singular point. So that is a singular point. So now what we have is we have to test our endpoints and we have to test our critical points in our function. So now the third part, add up here and critical points. So we want to test endpoints and critical points. In h of x. So h of -2 h of -1, because we got -1 from being a singular point or a critical point, and then we need to test h of 0. Remember that we got -2 and 0 from our closed interval, and h of x is this function. So remember, we are plugging -2 into our function. You have -2 plus 1 raised to the 2/5. That's equal to -1 raised to the 2/5, or the 5th root of -1 squared. That's the 5th root of 1, which is just 1. Okay? H of -1 is -1 plus 1 to the 2/5. Well, -1 plus 1 is 0, so we'll get 0 there. No fun. H of 0 is equal to 0 plus 1 raised to the 2/5. That's equal to 1 raised to the 2/5, which is just 1. So that gives us our information that we need. So in particular, we can now say that we would have the points. So we have points -2, 1. When x is -2, we got h of -2 was 1. We have -1, 0. Then we also have 0, 1. Now, we have two high points, or the two largest points were 1. That occurred at -2, 1 and 0, 1. So that means this is an absolute max. This is also an absolute max. And then 0 is a low point, so it's the only low point. So it's our absolute min, and because it's on the inside, we have it's a relative. Okay? And it's a relative min. What do I mean it's on the inside? -1. Note, -1 is in the interval -2 to 0. So because it's in that interval, that means whatever we got out would be a relative minimum, because we could take an open interval around that. Okay? So this is your final answer. Now, something else that will be useful for you moving forward will be the first derivative test, and that's helpful for the following reason. Suppose that C is a critical point of the continuous function f, and suppose that its derivative is defined for x close to and on both sides of x equals c. Then determine the sign of the derivative to the left and right of x equals c. If f prime of x is positive to the left of x equals c and negative to the right, then f has a maximum at c. So if your derivative changes from positive, that's right, from positive to negative, then you get a maximum at c. If f prime of x is less than 0 to the left of x equals c and positive to the right, then f has a minimum at c. So in other words, if it changes from negative to positive, you have a minimum at c. If f prime of x has the same sign on both sides of x equals c, then f has neither a maximum nor minimum at x equals c. So in other words, we can use the first derivative test to help us find our relative and absolute extrema for the function. Okay, so let's do that. Our given function is g of x equals 1 over x minus 1 over x squared. So it suffices for us to know what our domain is. Our domain for this function is the set of all x for g, where x cannot be equal to 0 because we cannot divide by 0 in there. Okay, now we need to find our derivative. Well, g prime of x, well, let's make that better. G prime of x is equal to, the derivative of 1 over x is -1 over x squared, and then you would be adding to that plus 2 over x cubed. And aside here, just to refresh your memories, you can rewrite 1 over x minus 1 over x squared as x raised to the -1 minus x raised to the -2. Now, differentiating this, we get that's equal to -1 x to the -2 minus -2 x to the -3, because you had -2 minus 1. That gives you -x to the -2 plus 2x to the negative third, which you can rewrite as this. Okay? Now, make sure you're comfortable taking derivatives at this point. So if you need to rewrite it, rewrite it. But make sure you take the time to understand what's going on. Okay? Now, it says up here, suppose that C is a critical point of the continuous function. So in order to use the first derivative test, we have to have our critical points. So that's why we needed to find the derivative. So now we find our critical points. G prime of x is equal to 0 means negative 1 over x squared plus 2 over x cubed is equal to 0, or 2 over x cubed is equal to 1 over x squared. We can cross multiply, and that gives us 2x squared is equal to x cubed. That's equals there. Now, that means if we divide both sides by x squared, we get 2 is equal to x. Now, that's one critical point. Note that we also get a critical point when we find out whenever our derivative is undefined. G prime of x is undefined. Since this is our derivative here, we know that that's undefined when x is equal to 0. So our critical points are x equals 0 and x equals 2. But wait a minute, we said that our domain was everything except for 0. So in fact, we have to reject this because it is not in our domain. We have x is equal to 0. X cannot be equal to 0. So we reject that. So our only critical point we get is x equals 2. Now we want to use the first derivative test to find our relative and absolute extrema. So let's do a number line. Let's set up a number line. Well, our interval. Note that here we had x equals 2, so we'll mark 2. And then we also have one with 0, but wait a minute, 0 we had to reject. So let's do a dashed line to let us know we can't include that. Now we need to check a number to the left and to the right of each point. We need to check a number to the left and the right of each point that we've marked. We've used our critical points. Even though we had to reject 0, we still want to check to see what happens there. Now, so note that here we would have a vertical asymptote there. So we really don't have to check. Okay. Now, we're going to check to the left of 2. I'll use red. We're going to check to the left of 2. We're going to check 1. What do we mean by checking? If in part 1 it says if our derivative is positive and it changes from positive to negative, that means we have a maximum. If our derivative is negative and it changes from negative to positive, has a minimum. So we're now choosing values to the left and right of our critical points to test in our derivative to see if our derivative is going to be positive or negative. So that's what we're checking. Now, let's see whenever we have g prime of 1, that's equal to, remember, this is g prime here, so plug that in. So g prime of 1 is equal to negative 1 over 1 squared plus 2 over 1 cubed. Well, negative 1 plus 2 is equal to 1. Okay, so the point is positive. The point, meaning the overall thing that we've learned here, is that g prime of 1 gives us 1, which is positive. Okay, now we need to check a number to the right of 2, let's check 3. G prime of 3 is equal to negative 1 over 3 squared plus 2 over 3 cubed. Well, that's equal to negative 1/9 plus 2 over 27, which would give us negative 1 over 27. Well, that's negative. Notice that it changes from positive to negative whenever we have x equals to 2. It changes from positive to negative. So what case are we in? We go back up to our first derivative test. We're in case 1. So that means that we have a maximum at 2. That's what that means. And in fact, since there are no others, then we get that 2, in fact, would be our absolute max. So let's write all of that down. Okay, so we have an absolute max when x is equal to 2, because it changed from positive to negative, x equals 2, and g of 2 is equal to 1/2. Now we're plugging 2 into our original. Notice that 2 was a critical point. So now we plug our critical points into our original function. So we get 1/2, because we're plugging it in here. You get 1/2 minus 1 over 2 squared, which is 1/4. So that leaves us with 1/4. And the reason we checked that, because we wanted to be able to write down our absolute max occurs at the point 2 1/4. And that concludes our notes here.